So this is the regular expressions clinic talk. I've given it multiple times, and apparently the interest does not die down. So regular expressions, for some of you it just may be line noise, and for some you may know all the intricacies of it, and this talk is sort of introduction to intermediate kind of usage of them as pertains to PHP specific implementation. So regular expressions, what are they good for? Well, you don't have to use them. I mean, you can just use regular string search and matching and extraction functions, but they're literal. They're fast, but not very flexible. With regular expressions, you get a lot of flexibility to find out whether a pattern occurs in the text, to find strings that match a pattern, and you can extract the strings matching the pattern and do all kinds of things with them. So some terminology before we go on. When I say a regex, I mean some sort of a pattern describes a set of strings that fit that pattern. There's also a subject string, what you're applying this regex to. And a match means a portion of the string that is successfully described by this regular expression pattern. And wow, yeah, this projector just killed some of the gray text that I had here. So a regular expression engine is a program that takes the pattern you give it, does some sort of compilation or interpretation of that, and applies it to a string. And there are different types of regex engines. Some are called DFA types, some are called NFA types, and this doesn't really matter what the distinction between them is right now, but the thing to understand about an NFA type engine, which is how most of them work these days, is that the engine goes along the string trying to match the regular expression, and sometimes it has to go back and try rematching again if it fails. And two basic things is that given multiple occurrences of the pattern in the string, it will always return the earliest, the leftmost match. So if you have the topic of the day is isotopes, it'll find the first top and return that to you. And if it has a choice where it could match something and not match something, it'll always favor a match. So just for color legend, we'll use red for regular expressions, yellow for subject strings, and purple for matches, just to separate them visually. Let's talk about syntax. Regular expression is composed of characters, and ordinary and special. The special set is a subset of ASCII. It's well defined for a particular implementation. And ordinary is just everything that's not special. These special characters are sometimes called meta characters, if you've run across that, or you might run across that when you read about regular expressions. Now, the most basic regular expression just consists of a single ordinary character, and it matches that literal character in a string. And you can concatenate characters together to match longer strings, obviously, like 1, 2, 3, and so on. But if you want to match an extended character that you don't necessarily want to type in, like accented or something like that, you can use hexadecimal notation with \x and then give it the hexadecimal digits for the character exactly. And if you want to match Unicode characters, you can put \x and then braces and a Unicode value inside. Now these meta characters, if you want to use one of them literally, you have to escape it with a \. Otherwise, it has special meaning to the regular expression engine that is going to try to interpret it as. But if you have a lot of these characters in your string, it may be tedious to \/ every one of them, in which case you can put a portion of the string between \Q and \E, which denotes the portion that is interpreted literally. So if you have \Q and E in this example, it'll match that string literally. It's not going to interpret those characters as special. Same with the \, but it depends on how many of those you have. Now, character class. A character class consists of a set of characters that you put inside the square brackets, and it will match one and only one of those characters. It's not like it's a string inside that is going to take and apply literally. You're saying, out of these characters that are inside the character class, I want to match any one of them. So we have, if you want to match an English vowel, we can put them all inside this character class in brackets. Or if we want to match surf or turf, we can say SOT at the beginning. Now, those character classes, they match characters, but sometimes you want to say, I don't match anything but this character or anything but a range of these characters. And the way you do that is you put a caret as the very first character after the opening bracket, and that means negation. It inverts the meaning of the character class. So if you have caret and then less than greater than brackets, it would match a character that's not left or right bracket. Any character that's not one of those. You can create character ranges, so it would be kind of tedious to try to describe all the, let's say, Latin characters from A to Z. You could type them out, A, B, C, and so on to the end, but it's easier to create a range. So you say A-Z, and it describes all those characters in the character set. It's basically an abbreviation for that. You can reverse the ranges, which sometimes can be useful, at least visually. You can have more than one range in the character class and then combine it with normal lists. So in this case, we're looking for a Latin letter, a digit from 0 to 9, or a colon as a character set is what we're trying to match. Some of these character sets I use so frequently that there are shortcuts for them. So we can have a word character, which is, uppercase, lowercase, letters, digits, and underscores. And in this case, word means like identifier, basically. It's all sort of Unix-based, so identifier is considered part of the word characters. \D is for digits, \S for white space. And then the capital versions of these are the opposites. They're negated character classes, not a word character, not a decimal digit, and not white space. Now, inside a character class, those special ones, the meta characters, most of them lose their meaning. You can just use them literally and not have to do anything special. But there are some exceptions. There's a closing bracket, backslash itself, caret, and a dash. And with those, you either have to use them literally. You either have to escape them with a backslash or put them somewhere they don't have special meaning. So like caret at the beginning has special meaning, but if we put it at the end, it loses its special meaning. You don't have to backslash it there. Now, dot meta character, by default, matches any single character out there. It's like a wild card, with the exception of a new line. And the reason it doesn't match a new line is, once again, goes back to Unix, where it was all line-based matching, and they didn't want to. You wanted to stop at the end when the new line was at the end, in the subject string. So we have this behavior where dot matches anything except the new line. And another way to think about it is it's equivalent to the character class that says not a new line. You have to use it carefully, because you might match something you didn't intend to. If you just literally say 12.45, it will match that string, 12.45, but it'll also match any of those, because dot matches anything, right? It'll even match a space, so you can have something ending in 1, 2 and starting with 4, 5, and it'll happily match that. Okay, let's talk about quantifiers. The contents of the text we're trying to match or validate, we're almost never quite sure about what's going to be there. So quantifiers kind of help deal with that uncertainty in the text. And they specify how many times a certain regular expression component has to repeat in order for the overall match to be successful. And the repeatable components that you can apply quantifiers to are things like literal characters, this dot meta character, a character class, those range shortcuts, which are just character classes, basically. And then a couple more things like subpatterns and back references, which we'll mention later. Now, these quantifiers are, there are 4 of them, and the first one is question mark, which means 0, 1. And it indicates that the preceding component is optional. If you say welcome bank question mark, it'll match either welcome or welcome with an exclamation point. Or, you know, if you're not sure if super strong should have a white space in the middle or not, you can say \s question mark, and it'll be optional. Plus, it basically says preceding component has to have at least 1 occurrence. So it's 1 or more. So if you want to match the word goal with any number of O's as long as there's 1, you can say go plus AL, and it will match any of those. Or if you're matching negative integers like -33, you're not sure how long those are, you can say -\d plus, and it'll try to repeat that digit as much as possible. And when you see things like not quote plus, which is a common occurrence, what that means is, yes, match any number of characters that are not quotes 1 or more times. The asterisk means 0 or more. So whereas plus says at least once, asterisk just doesn't place any restrictions. It could be 0 or more times. So you can have things like, if you're matching floating point numbers that have decimal component optional, you can say \d plus, then explicit dot, and then 0 more digits, and it'll match any of those. General repetition. So the question mark, the plus, and the asterisk, those have specific, you know, patterns that they require, 0 more, 1 more, and so on. But if you have something like it has to match from 3 to 5 times, then you use the general repetition operator. And you can omit either the end or the start of the range, or give it precise numbers. So if you can say \d and then the braces 8, it'll match exactly 8 digits. So you don't have to type out \d, and so on. If you don't have the second number specified, then there's no upper range set. That's how you say, like, from 3 plus, you know, 3 to infinity. And if you don't have the lower number set, it's obviously starts with 1, so it's up to a certain number. And you can use general repetition operator in place of any of the others, because that's the meaning they have, right? Like 0 or 1, and then 1 or more, 0 or more. It's just that it's so more convenient to use the shortcuts. If you have like questions pertaining to particular slides, ask them right away. If you have like general questions, we can hold those until the end. So greediness is a very important concept in regular expressions, and something that people run into time after time. And what it means in regular expression land is when it tries to match a pattern against a string, it'll match as much as possible up to a certain limit, if there is one. So if you have a regular expression such as PHP5 question mark where a 5 is optional, and you give it a string that has PHP5, it'll definitely try to match it, even though it has a choice over matching and non-matching. It's greedy, so it'll try to match that. Or if you have a regular expression saying from 2 to 4 digits, and you apply it to that string, it'll match the longest one because it's greedy. So it tries to grab as much as possible. Instead of 2, it'll get 4. So yes, quantifiers, they try to grab as much as possible by default. So if you write something like bracket, dot plus close bracket, which people sometimes write to match you know, HTML tags and things like that. The unintended behavior is that if you apply it to something like greediness surrounded by HTML tags, it'll match the whole string rather than just the I tag, because it starts with a bracket and then you say 1 more time any characters, and it's greedy, and since dot matches anything, it'll just go until the very end and match the closing bracket there rather than stop at the first one. Now, if the entire match fails because this greediness consumed too much, then the engine is sort of forced to give up as much as needed to make sure the rest of it succeeds, because it always tries for an overall successful match, right? It just needs to compromise then. So if you're trying to find words ending in ness, you'll write something like \w for a word character, one more of those, followed by ending in ness. And if you apply it to a string, on the first run, the \w plus portion will take the whole thing, because it's a word character. It'll match all of those. But then it still needs to match ness, so it's going to start giving up characters at the end until it can match ness. And if that actually occurs at the end. And sometimes you want to overcome this greediness, because that's not the desired behavior. And the way you do that is you want to make these operators non-greedy or lazy. And these lazy quantifiers, they try to grab as little as possible. It's just the opposite behavior. And if the overall match fails, then they go back and try to grab a little more and try the match again and keep repeating that until the overall match is successful or not. So the way you make them lazy is you append a question mark, right? And this question mark is different from its use as a regular quantifier, which means 0 more. So you can end up with like 2 question marks. And people say, what the hell does that mean? But it basically means 0 more times, but be lazy about it. Try to match 0 first. So if you have a lazy quantifier, if you had a question mark to the previous example, now it'll match properly because it's lazy, so it'll try to match as little as possible, and it'll succeed on the first tag. Another option to overcome greediness is to use negated character sets. I like to use those most of the time instead of lazy ones, just because they're it's clearer to understand what the meaning is when you read the regular expression. So you could turn the previous example into something like bracket, and then anything that's not a closing bracket character 1 or more times, followed by closing bracket. And this makes it explicit what you're looking for, and it's actually a little more efficient too. But you have to note that the second version will match tags that span multiple lines. And the reason is that when you say not a closing bracket, it means any character that's not a closing bracket. That includes a new line, right? So it'll actually match new lines inside those. If you want to do a single line version, then you have to exclude the new line characters as well. So we have all these things we can match, like character classes and quantifiers and things like that, right? But it'd be nice to do some sort of tests inside of regular expressions to check on things before matching and so on. And that's what you do with assertions. Assertions is an operator that expresses some sort of statement about the current matching point, and it doesn't consume any characters. It's just a test. The most common type of assertions is an anchor, where you anchor a match to a certain point in the string. And well, surprise, surprise, caret has another meaning, right? As everything in regular expressions. And with a caret, you anchor the match to the very beginning of the subject string. So if you want to match strings that start with capital F, you say caret capital F. And then it's going to look for that. And the opposite is the $sign, which is an anchor that matches at the end of the subject string or right before the string ending new line. Here's that Unix legacy again. So if you say \d $, it means that the string has to end with a digit. So if your string is top 10 or top 10 followed by a new line, either one of those will match this \d $, because $, has that special new line silliness. Sometimes your subject string is not a single line. It's like actually, a lot of times it consists of multiple lines, right? And if you want to do things like find all the lines that start with letter T, right, followed by one or more characters, and if you have the multi-line matching option set, which I'll talk about a bit later, caret will basically matches immediately after new lines, which means at the beginning of lines. And the $sign matches immediately before any new lines. So they basically work on a line-by-line level then. But if you have this multi-line option set, sometimes you do really mean the very beginning of the text or the very end of the text. And since caret and $sign now match on a line-by-line basis, you have to use other assertions. So you have \A that matches only at the very beginning, and \z with matches at the very end. And then if you want the $-like behavior with the new line stuff, that's a capital Z. So in this case, if we say \AT, it'll only match the first one, because that's the very beginning of the string, even though there are multiple lines there. Word boundary is another assertion, and word boundary is a position in the string where on one side there's a word character and on the other side there's non-word character. And remember that in regex land, word means letters, numbers, and underscores, right? So you have to kind of have to be careful with that. But basically, \b, it matches when the current position is a word boundary, and \B matches when the current position is not a word boundary. So if you have something like 2 surrounded by word boundaries, it'll match that as a word, right? It'll make sure that on one side there's going to be a non-word character somewhere which has spaces here. But if you wanted, for example, to look for digit 2 surrounded by word characters, you could do something like this, where you say find me 2 and make sure that it's a non-word boundary on both sides, so it's not like followed by space or something like that. It actually has Latin characters or digits or underscores. So subpatterns. I mentioned the subpatterns as one of those things that can be repeated by a quantifier. And what you do is basically use parentheses to group a part of the regular expression together, and that's called a subpattern. And then you can apply operators to it as a whole thing, which makes it convenient to do a lot of different matching things. So if you have regex like IS, and then you put land in parentheses, you can apply question mark to it, which means 0 or more, right? Optional. It'll match both is and island. So it basically is optionally followed by land, right? Or this regular expression, we have 2 digits followed by a comma inside parentheses, 0 more times, followed by 2 digits, and that means match a comma-separated list of double-digit numbers, right? We basically say there has to be at least one match of 2 digits, and the rest is optional. But they need to be repeated as a group. Now, by default, all these subpatterns are capturing, and what capturing means is that when there is a match, the engine takes that portion of the subject string that matched the subpattern and stores it somewhere in memory for future reference. And these subpatterns, the capturing ones, they're numbered, so it knows where to store them. It's numbered by counting their opening parentheses, right? So in this case, we have one subpattern nested inside the other. So there are 2 opening parentheses, there are 2 subpatterns. And if you run this regular expression against the string there, then the second one will match may, right? That's the nested one. Now, this capturing aspect, where it stores the matches for future reference, is not always necessary. Sometimes you want a purely grouping subpattern. You don't care that it actually matched. You know, you don't want to use this match in the future. and it requires more memory, more processing time to copy things around and so on, right? So you'd like to be able to turn that off. And the way to do that is to put a question mark colon after the opening parentheses of that sub-pattern. And that makes it just a purely grouping one, so you can apply operators to it. So if you have like box, and you want to match box or boxers, you can put question mark colon at the beginning of that sub-pattern, and then it'll still match, but it's not going to capture anything for the future. And you have to remember these non-capturing sub-patterns, they're not included in this numbering. So if you have like 3 sub-patterns, only one of them is non-capturing, then you really only have 2 capturing ones when you try to refer to them later. If you have a complicated regular expression, it can be kind of hard to keep track of all these numbers and which correspond to what. So it'd be nice to just be able to name a sub-pattern. You can do that if you use question mark capital P, and then you give it a name surrounded by brackets. You put this after the opening parentheses, and you have a named sub-pattern. They're still assigned numbers, but it's way easier to refer to them by names later. So if we're trying to match like integers, right, we can say, okay, we'll do question mark capital P, we'll give it a name number. And then when we run it against that string, we can access it using the name. Alternation, the pipe character, vertical bar, whatever you want to call it. So this alternation, the operator allows you to test several sub-expressions at a given point. It's basically an either or one of these. And these branches are tried in order from left to right until the first one that matches. And you can actually have empty branches. So you can say like A or B or empty for, nothing matches. And that can be useful sometimes. So if you have sailing or cruising, it'll match either one of those. One thing to remember is that alternation has the lowest precedence of any of the operators, so you often have to use grouping with them. If you have things like 6th or 7th sense, it'll match the word 6th or the phrase 7th sense, because even this concatenation thing with characters has higher precedence than alternation. So if you want to match 6th sense or 7th sense, you have to group you have to surround your test, the alternation test, with the, you have to put it into sub-pattern. And remember that the regular expression engine is eager. It'll try to return you match as soon as possible. So if you have something like camel or came or camera, and you have the string camera, it'll only return came, because that's the first one that occurs on the alternation list. It's the first one it was able to match. It's not going to try for the longer one in this case. Yes? The question was, does it depend on the order in the alternation? Yes, it depends on the order. If you put camera first, then it will definitely match camera. So put the more likely pattern as the first alternative, or the longer one is a better way to put it. You can't apply this 0 more, the question mark operator to assertions, but your branches, the alternation branches, can have assertions themselves, such as anchors. So you can have something like caret or my or your friend, and what it does, it tries to match friend at the beginning of the string, or after my or after your. So you can actually have like tests as part of your alternation. Backtracking. This is a big topic that's also very important to understand, so I'm going to spend some time on it. Backtracking in regular special land means if you don't succeed, you try again. And what happens is that when faced with several options that the regular expression engine could try to get to a successful match, it picks one of those options, but it remembers what the other ones were. And if this picked option doesn't lead to an overall successful match, it backtracks to where the decision point was, picks another option, and continues doing that. And this continues until either the overall match succeeds or it runs out of options. And these decision points where that happens, they include quantifiers and alternation. Two important things to remember about backtracking is that with greedy quantifiers, it'll always attempt the match first and then try to not match later. And with the lazy ones, it's the inverse. It'll always try to delay the match. And there are several decision points. It always go back to the most recent one in sort of like last in, first out order, right? So here's an example of backtracking. Let's say we want to match numbers ending with double zeros. And so we have this string 12300. Intuitively, that should match, right? So we start, and the first thing it tries to match is the one or more digits, according to the pattern. So it adds 1, adds 2, adds 3, adds 0, right? And adds another 0 because it says 1 or more digits. It happily consumes all of those. But then, string exhausted, you still need to match 0, 0. So it gives up 1 and tries again. Still can't match 0, 0. Gives up another 0. And then it can match the 0, 0 at the end. So here's an example of what happens when there is no successful match, no possible successful match. So it starts kind of the same way, 1, 2, and 3, adds those. Then can't match F there, right? So it gives up 3 and tries again. Still can't match F there. Gives up 2. Still can't match. But it can't give up anymore because it has a plus there, 1 or more digits, right? It's a restriction. So it fails. But in the process of this failure, it had to backtrack and do all this unnecessary work, right? So disabling backtracking can be useful. And the main goal with that is to speed up these matches that should fail as soon as possible, like in the previous example where we matched 1, 2, 3, and there's no more digits left. Just don't try to do that. And this matters a lot, especially with nested quantifiers, as we'll see. So there's this thing called atomic grouping, and if you put question mark greater than followed by any regular expression, it'll treat that regular expression piece as a single atomic token, and no backtracking occurs inside it. All those safe states, all those decision points that it normally does, it just forgets them. It just throws them out the window. So if we put that in the previous example, we say question mark greater than, and then put this 1 or more digits inside there, it will lock up all those available digits on the first run. And then when it can't, and when it tries to match after that, it will fail right away if the next 2 characters are not FF. So it disables backtracking, it fails as soon as possible, and useful in this case. The atomic groups they're not capturing, so don't try to refer to them later. These atomic groups, the regular expression there is just an arbitrary regex. It's you can use whatever you want inside there. You can nest them if you want, but there is a simple way to sort of do the same thing is to use a possessive quantifier. They're simpler to understand and to use, but they only apply to a single repeated item, only to a single quantifier. So to make it quantifier possessive, you append a single plus, which is another reuse of a character, right? So if you want to make repetition like 1 or more, if you want to grab 1 or more digits and make it possessive, you add another plus, then you say \d plus plus ff, which is the same as the atomic grouping, where if you put it inside the parentheses with the question mark greater than. And so the other ones are, yes, asterisk plus, question mark plus, and the generic operator plus. And they're always greedy, of course. They try to grab as much, try to lock up as much as possible. Now the thing about this, when people see this, like, oh, that's awesome, I'm going to like optimize all my regular expressions. I'm going to try to lock everything up as soon as possible and not, save on the speed and memory and all that stuff. But you have to keep in mind that atomic grouping or possessive quantifiers, they actually change the meaning or the outcome of the match. So if you have a string like A, B, C, D, E, F, if you just have one or more word characters followed by D, it'll match A, B, C, D. But if you put another plus to make it a possessive quantifier, it'll not match at all. Because on the first run, that one or more word characters will grab the whole string, and then it still needs to match D, and it can't go back because you disabled backtracking. And you're stuck. Back references. So back reference is an alias to one of those capturing subpatterns. I said when you want to refer to it later, this is how you do it. It matches whatever the one you're referring to has matched earlier. So for example, if I'm matching words that start with RE or LE and end with the same thing, I want to make sure that they match, we can say match RE or LE at the beginning, capture that, then match one or more word characters, and then \1, saying match again whatever the first capturing subpattern matched. So that way, you can match words like retire and legible, which start and end with RE or LE, but not the other ones. And if you want to refer to a name subpattern, you can use it with that syntax. Question mark, capital P equals name. Look around. These are assertions that test whether the characters before or after current matching point match the given regular expression. It's like an if statement. They consume no characters, they don't capture anything. And there's look ahead, which is for what comes after, and look behind to see what just was before there. So a positive look ahead with a question mark equal tests whether the characters after this at the current matching point following that match the given regular expression. So in this example, we match one or more word characters, and then we stop and we say, is there a colon following this? If there's a colon, then go ahead and match the rest of it. So it's like an if statement. And it'll match this string, but this colon one will end up in the second subpattern, because remember that these tests don't consume anything, don't capture anything. So it'll end up in the second one. And the negative look ahead is question mark bang. So it says make sure that the characters after this current matching point don't match the given regular expression. So you can do things like fish, as long as it's not followed by ing. So it'll match things like fisherman, fished, but not fishing. So people say, well, why do I need this? Can't they just do like not I, not N, and not G after fish? It'll kind of do the same. But the thing is, like, it might work, but it'll actually consume more that's needed, because those they consume characters at the matching points. And it'll fail on if the word is shorter than 6 characters. So it's like fished. It needs to consume 3 characters, and there's only 2 after fish, so it'll fail completely. And you can do more complicated stuff like fish not followed by hook or ing, right? So positive look behind, this was for characters following current matching point, and this is for what's preceded that. The restriction on that is that these regexes have to be a fixed size, but you can have alternation like branches. So you can things like find bar as long as not preceded by foo, and that's the syntax you use for that. Sorry, not find bar that's preceded by foo, like in the example, my foo bar. If you want to do the opposite, test that the characters preceding the current point do not match, then it's a negative look behind. So you can do things like find bar as long it's not preceded by foo, so it'll match stuff like in the bar, but not my foo bar. Conditionals. So these let you use a regular expression as another sort of if-else statement to selectively choose between different types of matches. So there are three kinds of condition. There's sub-pattern match, look-around assertion, and this recursive call thing, which we're not discussing today. But and you can basically have what happens in case of successful, if the condition is successful, and what happens in the case it's not successful. You can omit the negative one if you want. So sub-pattern conditions. This is satisfied if a capturing sub-pattern number n, which whatever you're referring to, has matched before. And this is useful for things like, matching words that are optionally enclosed by quotes, right? We can write an alternation saying, okay, quote, word characters, quote, or just word characters, but that's like repeating things, like it's not very cool. So you can do things like try to match a quote and then followed by word characters, like word boundaries, right? And then at the end do this condition that if this matched anything, match another quote. So it's a test saying if the first quote matched, there must be a quote at this point as well. There's a difference between putting a question mark inside or outside the grouping in this case, because the second one will always capture stuff, because the operator is not applied to the group, then it's applied to the quote. And the assertion conditions. So you can use these look around things, look behind, look ahead, to do similar sort of tests. So here we say match href equals, and then if the next character is a single or a double quote, so we do a look ahead, go ahead and match it, and then match this, match the quote, and then anything that's not space or space, non-space after that, and then match the quote again, because we have a reference to \1 there. And if there is no single or double quote following, then just match without quotes. So it's one way of doing that. I mentioned the multi-line option before, and here's how you can actually set or unset some of these options. The matching can be modified with these. You can put them right in the regular expression themselves. If you put question mark I, it enables case-insensitive mode. It's not going to care about the case of the characters. Question M enables multi-line matching for those caret and dollar ones. The S one makes that dot meta character match new line also, because by default it doesn't remember. And it's a useful one sometimes if you want to match new lines. X ignores literal white space. I'll show you what it's good for in a little bit. And capital U makes those quantifiers lazy by default, ungreedy. So you can make all of them lazy in a regular expression if you use capital U. You can combine them and unset them with a minus before them, so you can do things like turn on case-insensitive and multi-line, but turn off the dot matching new line and things like that. So comments. Sometimes you want to use comments in regular expressions. Here's a regular expression I wrote a long time ago, worked on Smarty engine. I don't work on it anymore. Don't complain to me about it. I should have put some comments in there. I don't remember what it does anymore. But the way you put a comments inside is you can use question mark hash, and then anything inside parentheses there will be considered a comment. But if you have that X option set that I just talked about, then anything after a hash that's outside a character class and up to the next new line is considered a comment as well. So you can basically, if you turn that option on, then you can split your regular expression on multiple lines and just comment each one if you need to, which is a lot more readable, I think, than using the other types of comments even. So this was just like syntax and rules and all that stuff. But in the day-to-day development, you frequently run into the same things you kind of need to do, and it's useful to have some sort of like a toolkit that you can pull out a certain pattern out of and apply to this solution. And also how to avoid certain problems when dealing with regular expression. So the first thing that is important to understand is that matching is different from validation. When you try to match something, or extract or whatever, you have to account for boundary conditions. Like if you're looking for a certain set of strings that is described as regular expression, you need to know what the boundary conditions for that are, where that can occur. And then when you validate, let's say with the same regular expression, your boundary conditions are pretty much known. It's the whole string that you're validating, right? So if you're trying to match an English word that starts with a capital letter, yeah, you can say like, okay, capital letter from A to Z followed by lowercase letters, dashes, and apostrophes 0 more times. You have to put boundary conditions in, which are the word boundaries. Otherwise, it just may match part of a word, right? Even though it matches that regular expression. If you're trying to validate that's like somebody submitted a form and you have a string and you want to make sure that it's an English word starting with a capital letter, well, you have to make sure it's the whole string. So you have to put caret at the beginning to anchor it at the beginning and dollar at the end. Otherwise, you may only validate part of the string that matches it, right? You want to make sure that it's the whole thing. So don't forget those anchors for validation. I already talked about dot a little bit. Just remember that it's a shortcut for not a new line, so it'll match anything. Some people just put a dot anywhere when they want to match any character, right? But if you think about it a little bit, it's good to be a little more explicit. If you're trying to look for letters, don't just put dot. Put actually letters. Like I'm looking for letters from A to Z. Talked about that. Yeah, negated classes. Try to use those. They're a little more clearer than lazy quantifiers. And remember that lazy quantifiers use backtracking, so it does this unnecessary work sometimes. If you use negative character classes, they try to match right away and lock up as much as possible. So another problem that people run into is this unlimited repeats, which when you have an inner repetition or an alternation combined with an outer one. So if you have like asterisk plus or plus asterisk and other stuff. What happens there is that if the initial match fails on the first run, it goes back and backtracks and tries to split up the string between those two operators. And the number of ways how it can split up that string grows exponentially. And it probably gets worse when your inner one has a dot, because dot can mean anything, can match anything, right? So PCRE engine in PHP, it has an option like optimization that helps in certain cases. It also has like a hard limit for backtracking. I think it's 100,000 million, something like that by default. But the best way to solve that is just prevent unnecessary backtracking before the engine has to do it for you. I use those possessive quantifiers or atomic grouping. So in this example, let's say we're matching a sequence of words or spaces inside a quoted string. So we have like word characters or 1 or 2 spaces, and then we have a quoted string, right? So we have a plus inside and an asterisk on the outside, which is one of these cases for unlimited repeats. So when you apply it to a string that'll match, like that has quotes at the beginning and end, it'll match as quickly. But if you omit the final quote, it'll run 35 times slower, just because it starts backtracking and splitting up the string and trying to do this matching and things like that. So the way we solve that is we use a possessive quantifier on the outer one. We'll just say, as soon as you matched words, word characters or spaces, just stop there, don't go backtracking. If the final quote doesn't match, that's it, the match fails. Extracting markup. So these are things like, I want to restrict the markup in my comment box that people can type stuff into. I can only want to let them use bold, italics, and other stuff. So the PREG match all function that you can use it to grab marked up stuff, but if you want to tokenize and process them separately, I like PREG split better. So you do things like I have this string and I want to split it into tokens and non-tokens, and so I have match, opening bracket followed optionally by a slash, and then a tag name, and optionally followed by a slash at the end and things like that. And I tell it to don't give me empty pieces back, and also capture the actual delimiters that I described here. And what you get back is like an array of tokens and tags and non-tags. And if you want to restrict markup, like I said, you can use things like strip tags, which has limited functionality, and it just strips everything except for certain ones, but then it doesn't deal very well with attributes and things like that. You can use some sort of custom tokenizer, or another way to do it is like with regular expressions using the callback feature, where this basically the same regular expression as I showed before, and you say run a preg replace on it and do the callback, and what happens is as it matches these tags, it invokes this function, and you just do some testing and validation there, saying is it one of the allowed ones or not. And if it's not one of the allowed ones, just sanitize it, return empty string back. Otherwise, sort of make up the nice tag that it matched. This will be, you can download the slides later. I think we're getting close to the time. Matching numbers. The integers are pretty easy. You just match one or more digits, or remember the boundaries, so the word boundaries. Floating point numbers, you can have things like integer dot fractional or just dot fractional. Both of those cases can be covered by this regular expression here, where you basically have a fractional part that always occurs and then preceded by integer one, optionally with some conditions there. You can match both integers and floating point numbers at the same time. You can use either alternation to say this floating point pattern or the integer one, or try to be masochist and combine them into one like that. You can prepend plus minus question mark character class, so that if you need to match signs. And these word boundaries, the assertions, you can substitute them by more appropriate ones depending on where you need to match numbers in. So quoted strings is another interesting one that people try to do. And it's easy if we want to match a string that can't contain other quotes inside, right? Because we just say quote, not a quote 0 more times or 1 more times, whatever, and then closing quote. But if you want to match strings that have escaped quotes inside, that's something different. And so you can use something like this. I'll split that up. So we're matching an opening quote, right? And then we have a component. So I like to think of these sub-patterns as components. So a component it's a segment without any quotes, so not a quote 1 or more times, or it's a quote that's preceded by a backslash, and we're using this positive look behind. And the reason I have to put 4 backslashes there is, you can ask me that afterwards. But trust me, that's what you need to do. A quote preceded by a backslash, and then this component repeats 0 more times without backtracking. Remember, we don't want to let it try to split up the string and go crazy if it can't match, so we lock it up as soon as possible. I think I have like 5 minutes left, so let's see what we can go through. Oh yeah, people will say, how do I match an email address? So the complete regular expression is about a book page long, and it was generated by a Perl program. So Jeff wrote a Perl program that generates a regular expression that matches email addresses. Of course, email addresses are very idiosyncratic, and I think the only real rule is that it has to be an @ sign somewhere. If it has an @ sign, it's a valid email address. Trust me. Phone numbers. So let's say you want to match US, Canada style phone numbers with all these possible variations of those. Let's see. I think I'm running out of time. You can take a look at this when you download the slides. Here's another explanation of what that does using multiple things we talked about today. But let's just finish with this. Don't try to do everything in a regular expression, right? If you'll just go crazy and like, I run preg match and it's just a string inside, you know, or something that can easily be done with one of the string functions in PHP. And because those have one purpose and one purpose only, they're usually much faster and easier to use than if you apply a regular expression engine for simple stuff. For anything that's more like uncertain and complicated, regular expressions are great. Really understand how backtracking works, because it'll save your ass at some point. Be aware of that context of where matching occurs. Don't just think it's like in an empty space. There may be something that comes before or after your match, so use those boundary conditions or assertions of some sort. And capture only one you intend to use. Kind of a green philosophy here, right? Because all those subpatterns are capturing by default. So sometimes in regular expressions, you do end up putting that question mark colon to make them non-capturing, and you have a whole bunch of them, but that's fine. Don't use single character classes. So don't put like open bracket B, close bracket to match letter B. It only makes things more complicated. Lazy or greedy, be very specific about what type of matching you need. Just help out both the regular expression engine and the person who's going to be reading and trying to understand this regular expression later. And put that most likely alternative first in the alternation list. So think about how to do this stuff. There are a number of tools that are helpful when you work with regular expressions, both on the web and like things you run on your desktop. I'm not going to go through them all, but you can do things like debug your regular expression and step through them and see exactly what match is and things like that. So it's some pretty cool stuff. So the link to joined in is there if you'd like to leave any comments. That page also has a link to the slides where slides are up on SlideShare, and the link is in that joined in page, so it's just a little motivation for you to go there. Thank you for coming. And if you have any questions, I think I'm out of time, but you can just ask me. I'm going to be around.